Hi guys, welcome to Learn Electronics Repair. This video is sponsored by PCBWay, and thanks to their kind sponsorship we've been looking at a number of different inexpensive projects, DIY electronics projects that we can build, and we're building test equipment because that's what we want to do. We want to fix things, yeah? So today I wanted to have a look at another inexpensive, easy to build project, and this one is a Signal Injector and Tracer. So this little device will basically generate a square wave signal that you can inject into amplifiers, audio circuits and even radio frequency circuits, because although it's generating square waves at a set frequency, lower than radio frequency, it generates lots of harmonics, and that means that those frequencies will be picked up by, for example, radio sensitive circuits, radio receiver circuits. So this is a really useful device to build, and this one actually is dual purpose. So with this one we can either use the probe to detect a signal within a circuit, and that signal basically via this switch is amplified and comes to the little earphone or speaker, or we can use it with a switch in the other direction to generate a signal that's injected into the circuit. And you can build a pair of these if you like. So you can build one to use as a injector and one to use as a detector. I had a look around on PCBWay's website and I couldn't find any shared projects, which are ones you can basically download the PCBs for, that were actually for signal injectors and detectors or receivers. So I had a look around on the internet and I thought, let's see if we can find a very simple device, something very cheap to make. We'll build the circuit on Vero board, we'll test it, and then let's design a little PCB and we can upload that ourselves. So this can be the LER Signal Injector Tracer, and then that will be available on PCBWay for people to order the PCBs. The circuit I settled on was this one. There are many circuits out there, a lot of them use NE555 timer, but this one just uses 2 NPN transistors, and to be quite honest there's nothing critical about this circuit. We have 5 resistors. We have the 2 transistors. This is using BC109C. I don't actually have any of these transistors, but they're easily available on AliExpress and there's lots of alternatives. So I'm going to use an alternative. And this is running on 9 volts, but in fact, actually, this circuit can work on quite a range of voltages. So we should be able to run it from a little circular cell type battery, something small, 6 volts, 12 volts, 9 volts, it doesn't really matter. All in all then there's 5 resistors, 3 capacitors, 2 transistors and a switch. This shows 2 switches, but I'm actually going to use 1 switch, and a little speaker. Although I didn't design this circuit, this is on the internet in many places. Nobody seems to have or own the copyright to it. I suspect this is very, very old. This circuit probably was designed and even back in the 60s or 70s, something like that. That's when these transistors were certainly the common types used by hobbyists. I'll show you the circuit online, and let's have a look to see how we're actually going to build it. This is the actual circuit on eWeb. Hobbyist's website explains how it works, and if we look around we'll find the same circuit on here. DIY electronic projects for free, 310 projects, and it's the same circuit here. And I even found it here, but in this case they don't have the switch and they're just using this as a signal injector, but it's the same circuit without the switch and the speaker. I'm going to build the version that you can switch between both, and this is the nicest schematic I could find in colour, so this is one that I've printed out. I'm going to build the prototype on Vero board, but this time I'm going to try to make it as small as I possibly can. And to do this I think it's best if we spend a little bit of time just trying to plan out the layout on the Vero board first. So if you look at the circuit, basically you have ground, so this is one strip of the Vero board. We have the base circuit, that's another strip. We have the collectors, obviously the transistors are 3 pins, so the third pin needs to go onto the variable. That's another strip. And then just about every other component goes to here. So that's a fourth strip on the variable board. So it looks like we should be able to build this using just effectively 4 strips of the variable board, okay? So let's see what we can do. So we're going to use a piece of graph paper to represent the strips, if you like, okay? I'm going to put the probe at this end because that's how the circuit doesn't kind of work that way. So I'm going to give myself a bit of space to do this. Let's start over here somewhere. So effectively this can be strip A, B, C and D. And then we'll come across here 0, 1 and so on. Yeah, that's the actual rows. Yeah, numbered backwards, but I really don't care. Okay, so the first thing we need to do then is have a connection that goes to the clip and to the probe. So we want one connection here, one connection here. Okay, the circles represent connections, and then this will be our clip, and this will be our probe. Yeah, we have that. After that then we have a capacitor. So the capacitor needs to go into a hole here. We need to cut a track on the PCB, and then the other end of the capacitor can go here. So that cross is a cut track. And then here we have our capacitor, and the capacitor is 1 nanofarad. So that's a 1 nanofarad capacitor goes there. After that you can see we've got a resistor, or in the same place you've got a resistor, so we need to connect the resistor, and then we have the base collector emitter of the transistor. So we need another hole for the resistor, and that goes up to row D. So row D, this effectively is your supply voltage, okay, and row A is your ground. So this is row A, this is row D. Yeah. Let's put our resistor in. So that's a 2.2 meg resistor in there, and then we've got the transistor. So we need 3 holes. So transistor goes in 1, 2, 3. Okay. After the transistor is the other capacitor and the resistor, so we need to put these in. So the capacitor will go from here, and we'll figure out where it's going to go in a bit, and the resistor can go from here, or vice versa actually. Oops, sorry, no, not here. I've put the wrong points. That is the base, it's not there. The resistor goes from the collector, which is here. Okay, so that's the resistor. So let's put them in. Resistor. Well, this is just making sure we don't get mixed up. Emitter, base, collector. Okay, the resistor goes here. And that one is a 10k. Yeah, this is where the capacitor goes from. And what comes after that? Well, we next have the base of the other transistor, but in actual fact we do need to cut the track so it's not shorted to this base. So that was quite handy. That is a cut track. Yeah. After that comes the base of the other transistor, and there is a capacitor in between the two. Now the capacitor actually goes from the collector of this one to the base of this one. So that is their collector, and this is the base of the other transistor. This is where the capacitor needs to connect to, okay? So this then would be the base, collector, emitter. So let's just draw them in. So again, emitter, base, collector, and now we have a capacitor from here, the base, to the collector of the other one. So that capacitor is going to go there, and that is a 1 nanofarad. Okay, and there's our next transistor. Emitter is already on ground where we want it to be. Now the collector, we don't want it shorting to the collector of the other one, yeah? So we have to cut another track. So this cut track is going to go there. Okay. What else do we have missing? We have another resistor, and the resistor goes from effectively this end of the capacitor and the base. We could have put it this side of the transistor, but since I've drawn it, we'll put it on the other side. Okay. That is another 2M2 resistor. Now we just have this part of the circuit. So the transistor collector goes to the switch, and then on the switch itself we've got the 2 other resistors here and the speaker. So I think what we can do is mount this stuff on the switch itself, yeah? So we just need, coming from here, one connection from the collector there, and one connection going to the other end of this capacitor, which we said we weren't sure exactly where we were going to put. So we have one connection here. Well, it's going to be underneath the resistor, so let's put it here. Okay, so that will now go to the switch. Yeah, that's effectively the first pole of the switch, the moving pole. Okay, then from here we have basically a 10k resistor. We have another 10k resistor. Okay, and we have from this one, we have the other end of this capacitor. So the capacitor can also go on here, which is another 1 nanofarad. And this point here, we'll call it A, will connect back to the board where this capacitor was on the base, and we left a space for it somewhere. We actually left a space for it there, okay? So that there is going to point A. And that's it, we have everything. We have everything, apart from the battery needs to be connected. Well, that ain't really a problem because we already have space here, and we can put a space here. So that is our circuit on 4 strips of ferro board, effectively. How long is it? 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 12 holes long, basically. 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. I was right. So how's that look on our bit of Vero board? Well, there's a bit of Vero board. Let's have a look. So 4 holes high and then 12 long. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So basically a bit of Vero board like that is big enough to build our circuit. Okay. I'm going to try use one of these. So this is like a little bleeper speaker out of a old ATX PC case, and I'm thinking that we can actually, if we make the Vero board a little bit longer, we can stick that on there with a bit of glue. Okay, and we can make it a bit longer this way, and I'm sure we could put like one of the little 12 volt or 6 volt pen light type batteries that are probably no wider than this, and we can make the thing about so long with the battery built in already. The switch and the components up here, I think I'll use another bit of Vero board, so effectively sandwich this in between, and then that means I can actually put the switch on the other one. I think that's what we can do with it. And I'm pretty confident I can actually use one switch that will switch the power and switch it between inject and trace. One other connection I guess I didn't mention, and that is that obviously your buzzer, your little speaker, goes here across this resistor Okay, and then this end here goes to B, which is basically back on here, which is where the power connects to. And we have plenty of spare holes to connect to, because this top rail is all the voltage rail. So we can connect B back to anywhere on this rail, really. B. That's what we need. Once we've built the prototype, we can then design a surface mount PCB, and let's see how small we really can get this as a project onto PCBWay. I'm thinking we may be able to use something, again, like a sort of pen light type cell, and maybe make a very small circular PCB, probably not much wider than this actually, with surface mount transistors and capacitors. I think that will actually work, and maybe even make a device that is not much longer than the depth of this plus the battery and the switch. Yeah, I'm going to fix this on here, so I'm going to leave a little bit of space in front where we can put the probe. I'm thinking of having the probe actually built onto here, so I'll leave like a couple of holes spare there, and I'm initially just going to use the entire length, and then we can cut it off once we know how long the battery is, and hopefully the battery holder will fit onto here as well. So to get us as small as possible, initially I'm going to use the Dremel and actually cut the strips so they're as close as I can either side. Okay, I have my long thin bit of strip board, a little bit scuffed here and there, but this is where the battery is going to go, so it doesn't matter, to be quite honest. So let's put this together. I have all the parts I need in here basically, so I have the little speaker, I have a little switch which is a double pole 3-way, ideal for what I'm going to do. The capacitors, so these are 1 nanofarad capacitors, so is this one, so is this one. What you need to bear in mind with this is that this capacitor on the input is the only thing protecting you from the high voltage that may be on whatever component you put your probe on. So you need to be aware of the voltage of this capacitor. This one is a 100 volt capacitor, and that's probably enough for anything you're likely to come across in an audio amplifier. But it may be safer to use something like this. So this is a 1 nanofarad 630 volt capacitor. It's a bit bigger and bulkier, so it'll make the thing a little bit bigger, but that is inherently safer. Another option would be to take, for example, a couple of these, but 2 nanofarad, and put them in series. Now, whereas with resistors, if you put 2 resistors in series, the total resistance is the sum of the two. So if you put 1k plus 1k in series, you get 2k. With capacitors, it's the opposite way round. So if you put a 2 and a 2 in series, you don't get 4 nanofarads, you get 1. But you do effectively double the voltage. So you could put 2 of these in series, use a 2 and a 2, and then you end up with 1 nanofarad at 200 volts. And that, I think, is going to be more than safe. But I'm going to use this one. That'll make the thing a little bit bigger, but it'll certainly keep me safe. So that's what I'm going to use. The other thing I've substituted was the transistors. So I don't have any BC109. These are BC108. There's some new ones and some pulls in there by the looks of it. And I also have a lot of BC107, mainly new ones, a few pulls. I've probably had these since the early 80s, or even maybe from the 70s, but I've tested a couple of them. I use the 107s. They're very similar. This is just a slightly higher voltage rating, but the wattage is the same. They're very similar. This has gain of 120. This doesn't. I haven't mentioned the gain. I printed these myself years ago, but I've just measured a couple of them. They were like 290 the gain, and they were both the same as each other, so I'm happy to use those. But I'm sure there's lots of other transistors you could use. One nice thing about these is they're in little metal cans, so it tends to help with the shielding. So if you have something like this, I would use it. Otherwise, if you just go and look on the internet for equivalents for BC109, you will. One other thing I'll quickly mention, like I mentioned most things quickly around here, these transistors come in type A, B and C, so you have like BC109A, B, C, and the letter following the numbers is effectively the gain, so the bind. So C is the highest gain. The two I measured was, they were about 290 each, so it's more than enough. And there's the first part of the PCB built. So we have space here for the speaker. This space is attaching the probe, so the probe will attach directly to this. A couple of things I've done. One is that I've removed all the tracks around here, because this point B coming in, effectively this is where any high voltage might be. The other side of the capacitor, we really are protected from that, but Vero board is not very good in high voltage situations. It has a tendency to arc over the tracks. It's anything, you know, above mains voltage, and even mains voltage is pushing it for Vero board, to be honest. This is just where I scuffed it, but it's complete. There's no connection through there anyway, it doesn't matter. I had to rearrange the layout slightly because these transistors, like the layout, the base pin is further forward, so they wanted to go into a triangular shaped hole formation. So I'll just draw this again. There's actually only 2 cut tracks necessary. I'll just draw the layout again, how it actually is, and then if any of you guys want to build one, it'll be easier for you. And there's the Vero board layout. So these blue lines, these are your 4 tracks. The dots just show where components are attached, basically. And you can see I've cut the tracks away here to isolate the high voltage. This is your probe, this is your clip, and then these are the various components. They're all marked, you can see them, so you should be able to construct this. There are only 2 cuts in the board, one here and one here. And then we have the wires going off to the switch, 3 wires. Switch 5 volts, switch A and switch B are those connections, okay? So these are the connections actually on the switch. Switch 5 volts, wire goes here. And these resistors, the little speaker, are actually mounted on the switch, as is this capacitor. So I haven't put it on the PCB, I'm actually going to put the capacitor in here, just for ease of construction, okay? So that's how it's going to be. So now we need to make up this little PCB with the switch, the 2 resistors, the speaker and the capacitor, but also the switch is going to connect the voltage. So this is the little switch we're going to use. It's a 3-position switch, so you can see it moves across, yeah? So if we put it to the left hand end and we flick it over, which obviously now is the right hand end, you'll see this effectively is the wiper, this terminal, the second one in, and you'll see that's connecting to there, but it doesn't connect to the other wiper on the other side, but the other wiper also connects to there. So in the off position, this wiper is connecting to here, and that's going to be nothing, yeah? Open circuit. So middle position, the wiper is no longer connected to here, it connects to the pin here, okay? And again, it's not connected to the other side, but that's connected to here. So if we put 5 volts on there, when the position of the switch is here, we'll have 5 volts power coming in on the wiper, and then we can connect the wiper to one of our resistors, whether it's the one that has the speaker or the one that has the capacitor going back to the input, okay? And then the next position, the last one, the wiper on this side now connects to the end, and the same on here, but again they're not connected to each other. So that can also be 5 volts. So if we put 5 volts on both of these, when the switch is in the middle position or this end, it will still have 5 volts. That's your on-off switch. When we go to this end, it switches off. In the middle position, it selects one of the resistors, and then the end position, it selects the other resistors. So that's how it's going to work. Let me put on a bit of paper for you, and then you'll see. So our switch has, we'll put the wiper there just so we know where it is, okay? Like so. And this here, these are the wiper, yeah? So this pin either connects to this one, or that one. When it's off, that's off. So for the power, we need to put 5 volts on both of these. Yeah, and that's connecting to nothing. So when the position is in 1, we'll call them 1, 2, 3. When it's in position 1 or 2, we have power. And that is out. So this is 5 volt from your battery. Or rather 9 volts I think we're actually using. Maybe even 12 volts. And that is out. That's your power switch, okay? Now, when it's in position 1, we want to select our speaker and our 10k resistor, which are in parallel. Those, yeah. You'll see one end actually goes to 5 volts. Okay. So what we can do is we have 5 volts coming in here, yeah. But that's the switched 5 volts, and this is the 5 volts we want, the switched 5 volts. So from here we can put a resistor and our speaker in parallel, and the other end goes to out, that, the 5 volts out, okay? So once we switch it on, we can select the speaker and we get the 5 volts on the other end. That's that bit, yeah? The other connection of the switch has the resistor and capacitor, and the capacitor goes back down to here. This is B. So on this one, this is where we're going to have the resistor and the capacitor. The resistor will go to out, 5 volts, yeah, and the capacitor will go to our circuit board. And the capacitor also comes from the switch. So from here, that goes to our circuit board, and it connects to here. Yeah, it connects to here. So that's SWB. So we can put that on our little diagram. So the capacitor, SWB. Okay. The other end of the switch, which is the wiper of this one, that's here, that goes to A on our circuit board, or as we called it, SWA. So the wiper here goes to SWA. And that's all we need to do to wire the switch up. Okay. The only other thing we need is obviously the out effectively goes to what we called here switch 5 volts. Yeah, so instead of calling it out, we'll call it switch 5 volts, even though we're not going to use 5 volts, we're going to use something else. But we can still call it that just for the hell of it. Yeah. Or maybe we should call it 9. Switch 9 volts. Switch 9 volts. I have this ready now. I've made a few little alterations, as you can see. I moved the capacitor one position further forwards, and that's because I didn't have enough space to put the speaker in, for the reasons I'd actually fitted a bit of a cut off piece of an IC socket here, and this is for connecting to the top board. So this is where the capacitor, this one, which is actually on the top board, connects to. Although there's 2 pins here, there's 2 pins, you'll see that the bottom one isn't actually connected to anything. It's been cut here. This goes nowhere anyway. And the reason for that is just for stability, basically, just an extra bit of stability. The same with the connector at the back. It goes across the whole board, 4 pins, but in actual fact, it only connects to the power. As you can see on here, the power, which is the 5 volts, and it connects to the collector of the transistor. So the switch and all these resistors, the speaker, are all on the top board. Yeah. So the power that is actually on here is actually power coming in. These wires, the black one is the negative connection to the battery holder, which I'm going to hopefully fit a little battery holder back here with the battery. And the green one is the crocodile clip lead. I've cut the end off an old scrap test lead, a multimeter lead, and then I cut this with a Dremel. So I cut through the plastic here first, cut it off. I could then slide the plastic off. I then cut this to the length I wanted it, and then I just used the Dremel to basically sand away at it a little bit, and then I found I could solder it very nicely. So that's soldered onto the PCB, so that is your probe. But I will put some epoxy resin in here to stop it breaking away from the variable board, basically. So that's the bottom board completed. The top board has a little bit of ingenuity, actually, a little bit of almost miniaturization with variable, yeah. So what we have on here, this connection is where the capacitor connects. You can see the capacitor there, actually, yeah, and it goes to here on this strip, okay. Both pins are connected to it, but as I said, only one is used. So this is where the capacitor connects, and that then goes back to this track, and this is connected to the switch. So you see I've had to kind of like fiddle around a bit, but I've actually got it soldered properly. The spacing of the legs let me do it, so there's no connection in here, there's no connection in under there, but it's slightly raised up, yeah. It might look like I've got a short, so I'll just prove I haven't. Continuity range. So the switch basically has 3 positions, and this is the wiper, yeah. So when the position of the switch is at this end, the wiper actually connects to this end of the switch, but this doesn't go anywhere. Make sure it's working. Okay, so the wiper is actually going to this end of the switch, but this end of the switch doesn't actually connect to anything, okay? That one doesn't go anywhere. The wiper, which is here, the second pin, you can see there, black wire, that goes to here, which is the collector of the transistor, okay? I think you can probably see it clearly. I just adjust the focus slightly. There, I think that's about the best I can do. So that's the actual collector coming in, and this goes to the wiper. So the wiper in this position is going to nowhere, yeah? And you'll see the wiper on the other side also connects to this end, which isn't going anywhere. The wiper on this side is actually connecting to the 5 volts going out. So this is your 5 volts going down to the PCB to power, yeah? The power comes in on these 2 poles. So if I move the switch over, in fact, if I leave it where it is, you'll see that from here I have no connection to the 5 volts going down to the PCB, yeah? It's open. Put the switch in the middle position, and we now should have power. Okay, red wire, power, yeah. And end position also, we should have power going to the board. Okay, so that's how the power switches through. The other side of the switch switches the resistors and capacitors. So in the middle position, it connects to this pin. And this pin, if you look, has a resistor going to this line, which is the 5 volts. So that's effectively switching this resistor and the speaker. If you can see, a little black wire underneath solders to here, and this goes down around the back of here, and this goes to the speaker. Okay. Now the speaker turned out is only 12 ohms, and if I want to run us off the 12 volt supply, the transistor, the BC107, can only handle 100 milliamps. So for now I've put a 100 ohm resistor in series with the speaker, which comes back to this line here. So this line here is all 5 volts, and it actually connects across here to 5 volts. Yeah, you can see it. I'll just show you on the test meter. So this is all 5 volts. It connects to the 5 volts coming in. Okay. When the switch is in the last position, the end, the wiper now connects to the end here. and this goes to the capacitor, which is there, and the other end of the capacitor switches to here, and it also goes to another resistor, and the other resistor is connecting back to the 5 volts. Okay, the other resistor actually being this one. So that top board basically has all of this circuitry, the 100 ohm resistor, and this is just to see if this will work, because obviously it will reduce the volume, but I don't think that's going to be a major thing with here. The 100 ohm goes in there. Pen's no good. Try another one. The 100 ohm is here, in series with the speaker. It may be a better idea to change this transistor for one that can handle more power. If we're running at 9 volts, which we may well do, we'll see, then you've probably got like 700 milliamps, but that's kind of like a continuous supply. Because it's oscillating, it's less than that. So we could put something a bit more powerful in there and then take the resistor out actually. So to put it together, we just put the wire through one of the gaps, doesn't really matter where it goes through. This is your positive connection from the battery. Something goes to sleep, probably my meter. And then the thing just clips together. Okay, so you can see that fits nicely in there. And that's as compact as I can make it as a prototype. Okay, let's see if it works. So it's switched to off, so I've marked off, trace, inject. Okay, so it set it to off. Now let's turn it on, trace. Oh, it's doing something, can you hear it? Sensitive to fingers. Let's stick a signal in. Let me get like a phono lead from my mixer, something like that, and a bit of music. Okay, so this is just connected to my mixer. Let's touch it with this. Well, it just seems to go quiet. Doesn't quite do what I expected. Let's pretty sure this is ground. No, that's not doing what I expected it to do. I think I need to have a look to see what it's doing. I'll use a little handheld oscilloscope. First of all, it's not stable. Yeah, doesn't like that. But there again, there should be like a shielded little holder, basically. So this is not an amplified signal, it's just coming directly out of my mixer from the PC. And there we have it, yeah. You can see, okay? That comes through here. So this goes into the first transistor base here. This is the collector. Yeah, look, it's amplifying, okay. That then goes into the base of the other transistor, which is here. Okay, and that should be coming out here. And I'm not sure this last transistor is actually amplifying properly. Let's have a look. Just go to the input and just alter the sensitivity, but it's on 5 volts now. Because that's the signal coming into the second transistor. And that's what's going out of it. And yet, all I can hear is like a kind of weird oscillation sounds. Let's put it into inject and see if this circuit actually sends a signal outwards. So, I'll just disconnect it from my mix for a moment. Okay. Right, so that's set to output. So it should be now sending a signal out. Well, there's not a lot going on, is there? In fact, it should be injecting a signal. It doesn't seem to be doing very much. So alter the sensitivity a little bit. I'm not sure exactly how big this signal is supposed to be. Well, that's on a half volt. It's there, but it's kind of like... I have the ground connected from the oscilloscope to the ground of the power supply coming in. That's just me touching. You see, like there's some sort of noise I'm picking up from something. Yeah. I also see it there. Okay, go back to trace. Well, the first thing I'm going to do is to remove or cut the tracks here, because touching it, he doesn't like it. Yeah. And I don't need this because the wires here are for the battery holder. Let's see if that helps. So we'll connect the power back up. Well, I can touch this now. Okay, let's connect an audio input again. Okay, there's definitely something playing. There's not enough of an effect there to be decisive. I can hear the beat. Can you hear it? What I'll do is, I think this idea of putting a 100 ohm resistor in series with the speaker was a bad one. So I'm going to take that resistor out. I'm going to find another transistor to use in place of this one. This is a BC337 general purpose NPN transistor, but it can handle up to 800 milliamps. I think that's going to be enough. So I'll replace the second BC107 with this, and then let's see what it does. So there's the bit of wire just tagged across the 100 ohm resistor. You can put this in. Let's see what it does now. I'll just make a little bit of space on my desk. Okay, and connect the power. Well, it's still making a squawky noise, but it isn't any louder. Goes off when you touch that. Let's give it a bit of music again. Let's have a look at what we've got coming in then. So this is the actual input, and you can see there's some music signal on there. I'm on 1 volt per division, so it's quite a small signal. Comes through the capacitor there into the base of the first transistor. There's a bit of a signal, and on the collector we have a much amplified signal. So that is clearly amplifying the first stage. Then that goes into the base of the second transistor here. Okay, we have lots of signal, but coming out there's just like these spiky bits, practically nothing. So it's like the second amplifier stage isn't working, and I've got a vague idea of why that might be. So let's have a look. So the second transistor, this is the collector, and this is connecting to the little speaker, which is about 12 ohms. So we can see our speaker is basically connected. Okay, and I say 12 volts, we're using 9 at the moment. So that connection's there. I think what's happening with this is that this resistor is the base resistor that supplies this transistor, and this circuit I'm pretty sure was designed to use like a high impedance headphone, which is why I have a 10k across it, maybe a very high resistance headphone speaker or something, and I was using quite a low impedance one. So I fitted a larger powered transistor so it should be able to handle the current. But I think what's probably wrong with this now is that there's not enough base current into this transistor to drive the current through the load. There should be enough current flowing down through here, at least to start this conducting, if you like, or give it a bit of bias so that the signal here can actually turn the transistor on. I think that's what the problem is. I think this is too high a value because I'm using a low impedance speaker. So let's replace this with something quite a lot smaller. And then let's see if we can get it to work. Now, what should I use? Well, I probably want, I don't know, I might just put a potentiometer actually. What should I use a potentiometer? Yeah, but I probably want like a couple of milliamps or something flowing into this to get the thing going. So if we're using effectively 10 volts, near as damage, 10 ohms would give 1 amp. Okay, 100 ohms would give 100 milliamps. A 1k would give about 10 milliamps. So a 10k here would give about a milliamp. I'm going to put a 10k resistor on there and let's see if that actually gives us some sound. I mean, we can always play around with the value, but I think we might be onto, or I may be onto, and I hope you guys, well, some of you are probably following me and some of you are probably shouting at me, yeah, but that's the way it is. Comments below, guys. I'll get a smaller resistor in there and let's see what it does. We now have a 10k base resistor on the second transistor stage. Shall we see what it does now? Ah, sounds different. I think you can hear like music, sort of. Let me try something with a bit of a beat. Oh, definitely. There we go, let's try something. Yeah. Hear it? Let's transistor's getting too hot. I could smell something funny actually. So that transistor is like too hot to touch practically. So that is too much for that. Can we make this work with this lower impedance speaker? Well, we could try again with a higher value resistor than the 10k that I put in. That would reduce the base current here. And I hope the transistor is still okay. I think it is actually. That would reduce the base current into here, and it should reduce the temperature of the transistor, but that kind of depend on the current it's drawing through here. Let's give it a go for the fun of it. I'll put a 47k in. Okay guys, here we go again, yeah. So I now have a 47k base resistor. Maybe my 10k was a little bit ambitious there. Let's see what this does. And I think this time I'll get a thermal camera on it as well if it makes any sound. Let's try it first and see if we can actually hear any music playing. I'm sure I can hear the beat. Let's see how hot that's getting. Okay guys, here we are. I have audio connected. I need to connect the power. And it's not getting hot. Not particularly. I mean the transistor's there. Let's have a look. But, oh, it's still 50 degrees. And the problem is now you can't really hear the audio to say you have a signal. Before we had like a beat, now we really don't have a beat. I think I have to go back to the drawing board with this one then, because the speaker I have is a low impedance speaker and this doesn't like it, yeah? And that's before we figured out why it didn't seem to oscillate. So so there must be some way to make a PCB signal tracer that actually works. Yeah, maybe the answer's being staring me in the face all along. And there we have it, the PCBWay Signal Tracer pen built out of a PCBWay pen, which the ink had run out of. So, how do we use it? Well, basically we need some little speakers like these. These are the ones I use on my PC. You can get these which comes with a little mains power pack, and you can get battery powered ones which would be even better. But even so, the one that comes with a little mains power pack, 12 volt power pack or 9 volt, is isolated from the mains via the little switch mode power supply or linear transformer. So they're quite safe to use with this connecting to a ground, but you should make sure you connect it to a proper safe ground. Yeah. So what we can do is, basically, we can leave that there. We can take our speakers and connect them to our tracer. Yeah, that's our tracer. And then when we touch this onto something with this signal, we should get a noise out of the speakers. Let's try it with my little signal generator. Okay, here is an audio signal generator set to sine wave at the moment. Let's see what it does. That works, yeah. So, our signal tracer works just fine. Let's try it with a little bit of music like I was trying to do originally. Ah! Yeah, we can hear it now, yeah? Yeah, working well. I have to have a bit of Northern Soul, of course, and I better keep talking over it, otherwise it'll probably give me some sort of copyright issue, yeah? But there you go, guys, that's working. And that's all you need to do to make a signal tracer pen. Yeah? If you're getting that stuff, yeah? About. Yeah? Okay, guys. So now, the only question is, can we make the signal injector? Yeah? And there it is, guys, the Learn Electronics Repair PCBWay Signal Tracer. Yeah, that is much better than the other attempt, without a doubt. This just goes to prove yet again you find these circuits all over the internet and they don't work. Yeah, or maybe it's just me unlucky. But of course, this was half the story we started with. Yeah, what about the Signal Injector? Well, I have another PCBWay pen. Slightly broken, this one, but the ink's run out. So, can we do it? What do you think? You know what's coming, guys. Part 2.